In mathematics, a principal bundle is a mathematical object that formalizes some of the essential features of the Cartesian product X times G of a space X with a group G. In the same way as with the Cartesian product, a principal bundle P is equipped with an action of G on P, analogous to X, G, H equals X, G H. For a product space, a projection onto X. For a product space, this is just the projection onto the first factor, X, G, X. Unlike a product space, principal bundles lack a preferred choice of identity cross-section. They have no preferred analog of X, E. Likewise, there is not generally a projection onto G generalizing the projection onto the second factor, X times GG, which exists for the Cartesian product. They may also have a complicated topology, which prevents them from being realized as a product space even if a number of arbitrary choices are made to try to define such a structure, or by defining it on smaller pieces of the space. A common example of a principal bundle is the frame bundle Φ of a vector bundle E, which consists of all ordered bases of the vector space attached to each point. The group G in this case is the general linear group, which acts on the right in the usual way, by changes of basis. Since there is no natural way to choose an ordered basis of a vector space, a frame bundle lacks a canonical choice of identity cross-section. Principal bundles have important applications in topology and differential geometry. They have also found application in physics, where they form part of the foundational framework of gauge theories. Formal definition: a principal G bundle, where G denotes any topological group, is a fiber bundle π px together with a continuous right action P times Gp such that G preserves the fibers of P, i.e., if ypx then ygpx for all Gg, and acts freely and transitively on them. This implies that each fiber of the bundle is homeomorphic to the group G itself. Frequently, one requires the base space X to be housed off and possibly paracompact. Since the group action preserves the fibers of π px and acts transitively, it follows that the orbits of the G action are precisely these fibers, and the orbit space P G is homeomorphic to the base space X. Because the action is free, the fibers have the structure of G-torsors. A G-torsor is a space which is homeomorphic to G but lacks a group structure, since there is no preferred choice of an identity element. An equivalent definition of a principal G bundle is a G bundle π px with fiber G, where the structure group acts on the fiber by left multiplication. Since right multiplication by G on the fiber commutes with the action of the structure group, there exists an invariant notion of right multiplication by G on P. The fibers of π then become right G-torsors for this action. The definitions above are for arbitrary topological spaces. One can also define principal G bundles in the category of smooth manifolds. Here π px is required to be a smooth map between smooth manifolds. G is required to be a Lie group, and the corresponding action on P should be smooth. Examples: the prototypical example of a smooth principal bundle is the frame bundle of a smooth manifold M, often denoted Fm or GL M. Here the fiber over a point Xm is the set of all frames, i.e., ordered bases, for the tangent space Txm. The general linear group GL N R acts freely and transitively on these frames. These fibers can be glued together in a natural way so as to obtain a principal GL N R bundle over M. Variations on the above example include the orthonormal frame bundle of a Riemannian manifold. Here the frames are required to be orthonormal with respect to the metric. The structure group is the orthogonal group O(n). The example also works for bundles other than the tangent bundle. If E is any vector bundle of rank K over M, then the bundle of frames of E is a principal GL. K. R. Bundle, sometimes denoted F. E. A normal, regular, covering space P. CX is a principal bundle where the structure group G equals pi 1 x slash p pi 1 c. Display style G equals pi underscore 1 x p underscore asterisk pi underscore 1 c. Closing curly bracket, acts on the fibers of P via the monodromy action. In particular, the universal cover of X is a principal bundle over X with structure group pi 1 x. Since their universal cover is simply connected and thus pi 1 c is trivial, let G be a Lie group and let H be a closed subgroup. Not necessarily normal. Then G is a principal H bundle over the left coset space G, H. Here the action of H on G is just right multiplication. The fibers are the left cosets of H. In this case there is a distinguished fiber, the one containing the identity, which is naturally isomorphic to H. Consider the projection pi S1 given by ZZ2. This principal Z2 bundle is the associated bundle of the Mobius strip. Besides the trivial bundle, this is the only principal Z2 bundle over S1. Projective spaces provide some more interesting examples of principal bundles. Recall that the n-sphere Sn is a two-fold covering space of real projective space Rpn. The natural action of O(1) on Sn gives it the structure of a principal O(1) bundle over Rpn. Likewise, S2n plus 1 is a principal U(1) bundle over complex projective space Cpn, and S4n plus 3 is a principal SP(1) bundle over quaternionic projective space Hpn. We then have a series of principal bundles for each positive n. O(1) S R n plus 1 R P n. Display style mbox O(1) 2s mathbar R caret n plus 1 2 mathbar RP caret n U(1) S C n plus 1 C P n. Display style mbox U(1) 2s mathbar C caret n plus 1 2 mathbar CP caret n SP 1 S H n plus 1 H P n. Display style mbox SP 1 2s mathbar H caret n plus 1 2 mathbar HP caret n. Closing curly bracket. Here S V denotes the unit sphere in V, equipped with the Euclidean metric. For all of these examples, the n equals 1 cases give the so-called Hopf bundles. Basic properties, trivializations and cross-sections. One of the most important questions regarding any fiber bundle is whether or not it is trivial, i.e., isomorphic to her product bundle. For principal bundles there is a convenient characterization of triviality. Proposition: a principal bundle is trivial if and only if it admits a global cross-section. The same is not true for other fiber bundles. For instance, vector bundles always have a zero section whether they are trivial or not, and sphere bundles may admit many global sections without being trivial. The same fact applies to local trivializations of principal bundles. Let pi px be a principal G bundle. An open set U in X admits a local trivialization if and only if there exists a local section on U. Given a local trivialization, phi pi minus 1 U times G. Display style phi pi caret minus 1 u to u times G. One can define an associated local section S u pi minus 1 u s x equals phi minus 1 x e. Display style S u to pi caret minus 1 u s x equals phi caret minus 1 x e backslash closing curly bracket, where E is the identity and G. Conversely, given a section S1 defines a trivialization phi by phi minus 1 x G equals S x G. Display style phi caret minus 1 x G equals S x C dot G. Closing curly bracket. The simple transitivity of the G action on the fibers of P guarantees that this map is a bijection. It is also a homeomorphism. The local trivializations defined by local sections are G equivariant in the following sense. If we write phi pi minus 1 u times G display style phi pi caret minus 1 u to u times G in the form phi p equals pi p phi p display style phi p equals pi p var phi p closing curly bracket, then the map phi p G display style var phi p to G satisfies phi p G equals phi p G display style var phi p c dot G equals var phi p G closing curly bracket. Equivariant trivializations therefore preserve the G-torser structure of the fibers. In terms of the associated local section S, the map phi is given by phi S x G equals G display style var phi S x C dot G equals G closing curly bracket. The local version of the cross-section theorem then states that the equivariant local trivializations of a principal bundle are in one-to-one correspondence with local sections. Given an equivariant local trivialization UI phi I of P, we have local sections C on each UI. On overlaps, these must be related by the action of the structure group G. In fact, the relationship is provided by the transition functions T I J equals U I U J G display style T underscore I J equals U underscore I cap U underscore J to G closing curly bracket. For any x U J we have S J x equals S I x T I J x display style S underscore J x equals S underscore I x C dot T underscore I J x closing curly bracket. Characterization of smooth principal bundles. If pi Px is a smooth principal G bundle, then G acts freely and properly on P so that the orbit space P G is diffeomorphic to the base space X. It turns out that these properties completely characterize smooth principal bundles. That is, if P is a smooth manifold, G a Lie group and mu P times G P a smooth, free, and proper right action, then P G is a smooth manifold. The natural projection pi P G is a smooth submersion, and P is a smooth principal G bundle over P G. Use of the notion reduction of the structure group. Given a subgroup H of G, one may consider the bundle P slash H display style P H whose fibers are homeomorphic to the coset space G slash H display style G, H. If the new bundle admits a global section, then one says that the section is a reduction of the structure group from G to H. The reason for this name is that the fiber-wise inverse image of the values of this section form a subbundle of P, which is a principal H bundle. If H is the identity, then a section of P itself is a reduction of the structure group to the identity. Reductions of the structure group do not in general exist. Many topological questions about the structure of a manifold or the structure of bundles over it that are associated to a principal G bundle may be rephrased as questions about the admissibility of the reduction of the structure group from G to H. For example, a 2n-dimensional real manifold admits an almost complex structure if the frame bundle on the manifold, whose fibers are G, L, 2, N, R, display style GL, 2n, mathbar, R, closing curly bracket, can be reduced to the group G, L, N, C, G, L, 2, N, R, display style mathroom GL, N, mathbar, C, subset mathroom GL, 2n, mathbar, R, closing curly bracket. An n-dimensional real manifold admits a k-plane field if the frame bundle can be reduced to the structure group G, L, K, R, G, L, N, R, display style mathroom GL, K, mathbar, R, subset mathroom GL, N, mathbar, R, closing curly bracket. A manifold is orientable if and only if its frame bundle can be reduced to the special orthogonal group S, O, N, G, L, N, R, display style mathroom so, N, subset mathroom GL, N, mathbar, R, closing curly bracket. A manifold has spin structure if and only if its frame bundle can be further reduced from S, O, N, display style mathroom so, N, closing curly bracket, 2, S, P, I, N, N, display style mathroom spin, N, closing curly bracket. The spin group, which maps to S, O, N, display style mathroom so, N, closing curly bracket, as a double cover. Also note, an n-dimensional manifold admits n vector fields that are linearly independent at each point if and only if its frame bundle admits a global section. In this case, the manifold is called parallelizable. Associated vector bundles and frames. If P is a principal G bundle and V is a linear representation of G, then one can construct a vector bundle E equals P times G, V, display style E equals P times underscore G, V, with fiber V as the quotient of the product P times V by the diagonal action of G. This is a special case of the associated bundle construction, and E is called an associated vector bundle to P if the representation of G on V is faithful, so that G is a subgroup of the general linear group GL. V. Then E is a G bundle and P provides a reduction of structure group of the frame bundle of E from GL. V. to G. This is the sense in which principal bundles provide an abstract formulation of the theory of frame bundles. Classification of principal bundles. Any topological group G admits a classifying space BG. The quotient by the action of G of some weakly contractible space e.g. I, E, a topological space with vanishing homotopy groups. The classifying space has the property that any G principal bundle over a paracompact manifold B is isomorphic to a pullback of the principal bundle e.g. BG. In fact, more is true, as the set of isomorphism classes of principal G bundles over the base B identifies with the set of homotopy classes of maps BBG. See also associated bundle, vector bundle, G-structure, reduction of the structure group, gauge theory, connection, principal bundle, G-fibration. Sources: Bleecker, David, 1981. Gauge Theory and Variational Principles. Addison Wesley Publishing. ISBN 0-486-445461. Jost, Jürgen. 2005. Riemannian Geometry and Geometric Analysis. 4th ed. New York. Springer. ISBN 3-540-25907-4. Hughes Moller, Dale. 1994. Fiber Bundles. 3rd ed. New York. Springer. ISBN 978-0-387-94087-8. Sharp, R. W. 1997. Differential Geometry. Cartan's Generalization of Klein's Erlangen Program. New York. Springer. ISBN 0-387-94732-9. Steenrod, Norman. 1951. The Topology of Fiber Bundles. Princeton. Princeton University Press. ISBN 0-691-00548-6.